Thank you. Good afternoon, everyone. I would actually like to start with a brief moment of silence for the few people that were lost in Baltimore today. We're all here, and as engineers, we dedicate our life to the safe passage of people and goods. You never want to see something like that happen, and I hate to start on a morbid tone, but fiber alignment is actually what allows us to design and innovate and work to save the world by sustainable solutions. This is the vehicle through which we achieve that capacity. So proper fiber alignment is how we avoid future catastrophes. All right, thank you. So this right here is what every engineer does not want to have, right? This is your traditional brittle failure of concrete. This is what happens when you don't have any reinforcement. You establish a predominant crack and your material fails. This is the comparison of what we're looking for with UHPC. We introduce fibers. In this case, I'm talking predominantly metallic fibers at a dosage to achieve strain hardening behavior. And that allows the member to crack multiple times, continue to carry load, and exhibit significant deformation. This would be your response of traditional concrete, right? I know this has been covered a few times in the last few sections. This is the behavior we're looking to exhibit with UHPC. We want to crack and continue to carry load and, in fact, carry more stress post-crack. So from that, right, we have a standard reinforced concrete model that all of us have, known and loved for many years. You have your compression block, and you have a tension response from whatever rebar you put in. Well, now let's consider what we're trying to do on a sectional level. With UHPC and the addition of steel fibers, we are taking advantage of the full depth of our concrete member. We have a response in a positive fashion, right? We are carrying tension below the crack and using the full depth of our concrete member. So here's just a quick example. There's been a lot of talk about the AASHTO guide that was just published. That is not free, and FHWA is. So all of the examples you see here are from FHWA. Thank you very much. You'll see this is a calculation that's in the appendix. They walk through how to apply the code in the sectional model, and it's using a gamma factor for fiber orientation of 1.0. So you go through the calculation, you follow through the mechanics, and you know what your capacity is. So they use 3 number 11 bars, which you could calculate is 281 kips of tension in the sectional response, approximately 60%. Now you have UHPC at localization, which is 185 kips of tension that we're carrying, all because of the fibers that are present. It's about 40% of your tension response in this member. The height of your member that's post-crack carrying tension is about 65%, right? We go from a compression block that might be 10% of your depth. Now we're using our compression block plus 65% in tension. In shear, you get a resistance from the stirrups that are present of 114.5 kips, which is 23.2%. UHPC, you have 380 kips of tension response carrying your shear load. That makes up 77%, right? That is a very large contributor to the capacity of this beam. There are many cases where you can now get away from shear stirrups, and that now leaves you with a purely fiber reinforced shear resistance. The whole point of why we're here in this session, fibers matter, right? That's what we're talking about. Fibers matter. So now I'm going to look at that same design example, but I'm going to use the gamma of 0.85. That's a 15% reduction, assuming that we have some misalignment, some segregation, any number of a million things that can go wrong. So you'll see that my moment capacity went down by 4.3%, right? We're using a sectional model, so the direct loss in linear contribution is not one-to-one equivalent of your loss in bending capacity, but still, if you lose 5%, that's a very significant portion of your capacity. So there's no change in the tension contribution you get from your number 11 bars, right? We have been testing steel rebar for a very long time. It's very stable. We have an adequately conservative model to reflect the behavior of steel rebar. Your tension from UHPC at localization, you get about 14% less capacity. Your height of your crack is about 1.6% taller. Even though UHPC performs really well once it's cracked, we want to keep as much of our section intact as possible. Shear contribution. Because of the model, using the modified compression field theory, you actually will develop less tension in your shear stirrups with UHPC if you have inadequate fiber distribution. And that's all based on where your predominant failure method develops. It depends on your beam size and many other factors. But what I want you to take away from this is the impact of fiber can actually impact what you think you're getting from your steel rebar. And then, of course, you have an impact to the shear resistance of your UHPC. This is all assuming a nominal 15% reduction. And now, after we've all been so happy that AASHTO released this code and we can design structures, this is the long paragraph that is basically a disclaimer that says, use this if you properly distribute your fibers. That's what we take away from this. You can only design with UHPC if you take adequate care to distribute your fibers. So just a very quick practical example. This compared two placement methods by qualified personnel, not myself, don't worry, but it was qualified personnel. They were both rational, reasonable methods from a mile high. If you looked at the structure, you'd think, okay, that's a reasonable way to approach pouring this member. They then saw cut parts of the member, and they tested them both parallel and perpendicular to placement. And you can see the results here. With the less adequate method, the difference was 28 or 43%. Now, I just showed you the impact of a 15% gamma factor that was kind of an engineer's judgment. I really want to put in perspective what the magnitude of fiber orientation can be. There are ways to do fiber orientation very poorly. Let's say you develop a predominant cold joint. You're not going to get the monolithic behavior of the material. You will not transfer load in the way that you're anticipating through your design model. And all day we have talked about very impressive and adequate methods to quantify fiber distribution. But if we can't get that in our structure, there's no correlation. We're losing that vehicle. The next thing to consider is the impact of fiber orientation is directly and exponentially correlated with height as well as complexity, right? I just compared for you in a rectangular beam that is relatively easy to pour. There's not a whole lot of complexity there. When we get into the places that UHPC can have its largest impact, well, this is a 54-inch tall bridge girder with a funnel that necks down for your web, opens back up, and now you have to coat all the strands in the bottom flange. It takes intentional care to get the orientation and the behavior that you want. It sounds like a lot of work, but when you consider that I just showed you the capacity of these beams, you're looking at a 30 to 50 or more % increase in capacity by this tension, right? It's not a novel amount. It's worthwhile to get this right, but it has to have adequate care and attention. So, thank you again, FHWA, for giving me free resources. This is an example that's in the guide as well. It's a 151-foot bridge girder. It's 4.5 feet deep. Quick math, that's 0.315 cubic yards per linear foot, or 47.6 cubic yards. And there are 48 strands in the bottom flange. The weight of the steel fiber is 12,500 pounds. And I believe we heard before that to properly model the behavior of those fibers, it could take a supercomputer. Well, it's because we have 1.8 billion fibers in this steel girder. We're accomplishing this behavior with 1.8 billion steel fibers that we want in the proper place, facing the proper direction. So now let's look at the shear critical section, right? We have a beam depth that's 54 inches. Your shear depth, shown in red here, is 49.2 inches. Your fiber contribution depth, that's 91% of your structure that is contributing from the steel fiber in the post-crack response. That's almost the entirety of your structure that you're relying on these fibers to be placed. And now the length of the shear, where your predominant shear crack and failure occurs, is at an angle, and it's 8'5" long, that predominant crack in this very specific instance. What does that give you? A width of influence as far as where you're pouring of 7'4". So at the end of your beam, that 7'4" is within your most critical shear loaded portion of the beam. 100 million fibers are contributing to that shear capacity that you're designing for here. And we hear preferential alignment all the time. But what does preferential alignment mean? We have some very intelligent people in here. We have PhDs and engineers and all of the above. But the people that are pouring the structures need to understand what preferential alignment means. Just like ultra high performance concrete, it's very subjective. So when I have a shear crack that's at an angle of 29 degrees, preferential is not necessarily laying down flat parallel with my strand. Now I'm not getting the perpendicular to the crack response where I have my actual mechanical behavior. So it's very important for us not to get caught up just saying preferential alignment. That is a very subjective term that, again, we have a very large community of experts, but there are a lot of engineers out there, and we need to communicate this to them so that they can use it. Next, I want to talk about your flexural critical section. Same girder, you're out at midspan. I call it critical section about 30 feet. We'll call it L/5, right? You have, your maximum moment, of course, set midspan, but there's an area of influence where you're nearing your maximum loads. You have a crack height of 28 inches in the UHPC section with a pre-tension girder. Critical fiber contribution depth, that's about 52%. Again, with regular concrete, that number is going to be 0. Your volume in that 30 feet is 9.5 cubic yards, or 351 million fibers. Those fibers have to be poured around 1,500 linear feet a strand, which is 250 square feet, not accounting for the individual strands and the added surface area of that. That is a lot of obstruction to your flow. Again, we're going to talk about what does preferential alignment mean here. Well, this is a sectional model, and when we're trying to resist our flexure, we do want that response that is perpendicular to the vertical axis. So preferential here can be aligned, but it shouldn't be assumed. It should be communicated. So now we're going to recap. You got a 151-foot beam. It's 1.8 billion fibers. You're pouring it all through a 3.5-inch thick web. I know we saw a couple presentations today about pouring through a much thinner area. It can be done, and you can achieve orientation, but we're talking about pouring almost 50 cubic yards, and in a production setting, people care about turning things over and doing it faster. So we're pouring 1.8 billion fibers through 3.5 inches of a vertical channel. We're encompassing more than 1 mile worth of strand with those 48 strands. That's a lot of friction, and that's a lot of obstruction. We have multiple preferential alignments. What we prefer is not the same everywhere throughout the beam. And the fibers can make up between 40 and 80% of your capacity. Does all this sound scary? I don't want it to sound scary. The intent is not to be scared away from using UHPC. This has been done successfully. This is a photo of a UHPC beam with strands. It has been tested and met the loads that were designed for. This is an alternative shape with corners and more complexity. This has been poured and used and carried load. We have waffle panels and we have pie girders. This has been done. It can be done. The intention here is just to talk about the care that's required to make design become a reality. And to do that, I'm going to talk about best practices, but I'm going to talk about it from a high point of view. I'm not going to talk about how you pour a specific member, but what can we as an industry do to educate those so that we can pour more UHPC? We can learn. This has been done. It's been done throughout America, Canada, the rest of the world. We don't need to limit our learnings or try something new for the first time. It has probably already been tried and already reflected upon, learned upon, and improved. Consult material suppliers or other industry experts, right? That knowledge and expertise exists, and if that specific instance doesn't, the knowledge to apply it and get it right or have a higher percentage of getting it right on your first try exists. And last, Perform workability tests and other critical rheology-related tests so that you know exactly what you have from your material in your given ambient condition. And that's the important one that people tend to forget. Your material can behave one way in a lab. If you're in a dry area, direct sunlight, wind, any number of conditions, your rheology changes. 2 hours of workability in a lab is not the same thing as 2 hours that it's sitting in a form with a very large surface area, or as it's taking an angle of repose and working down a beam. So as much information as you can gather ahead of time, there's strength in knowing. The next is prepare. I like to call it batch math, but with regular concrete, we turn loads over very quickly. A lot of places have multiple mixers, and you constantly have a flow of concrete. With UHPC, it's a little bit more care involved in the mixing process. So if you have a 5 cubic yard member, but you can only mix 4 cubic yards, you need to have a plan for the time in between to get the remainder of your material. Obviously, now we're talking about a 50 cubic yard girder. You have to have a plan in place to get the material and the what if something goes wrong, how do I do this? And then the last thing under prepare is mock-ups. Right now we have a pretty good example that exists with the French code. What they do is they pour a mock-up of the shape that they're going to put out and transport civilians, and then they take saw cuts from it and they compare it to theoretical molded specimens to ensure that we have the capacity that we're assuming in our design. Communicate. This is probably the largest burden amongst the people in this room, right? We all hold a high skill set. We're very intelligent. We're interested. We want to do these things. We need to communicate. What does preferred mean in this member? What is and is not acceptable, or what is expected? These are the communication things that can avoid a very upset producer, owner, engineer if you have a very expensive beam at the end. And the last one is to collaborate. We're going to need two-way feedback. We are still, as an industry, learning, right? We just learned about a lot of theoretical models and things that have been done, and they've been done 1 or 2 times. We have a long way to go to continue learning, and that two-way feedback is how we get better. And adjust as you go. Feedback is no good if you don't reflect and implement. And so what I'll leave you with is that success is not an accident, it is designed. You should approach pouring these beams with an intention. You should know how you're going to pour it, how you're going to achieve preferential alignment, how you're going to achieve the capacity so you can use less steel and build more sustainable and resilient structures. Thank you.